its degeneration scenarios at certain time instant. So there are multiple degeneration scenarios. For each of them, we have performance. And here E refers to what we call the speed oscillation energy. So that is what we are looking at in this study to understand the performance of the platoon. And I'll be talking about that in just a little bit. And then all the degeneration scenarios for a particular information flow topology, we have the performance, the probability, and we get the expected performance for a specific information flow topology. We do that for all possible information flow topologies at the platoon level. And then, for that, based on that, we choose the one which has the best expected platoon performance. Because this is an expectation. So for each IFT, you'll have an expected performance. You do that for all IFTs and choose the one which has, in fact, in this case, the minimum value because you're minimizing the energy. The probability is determined using a communication success rate model. And you see the reference there. I'll show the reference at the end of the presentation. And in order to do that, there are two aspects here. When information flow has unsaturated conditions and when information flow has saturated conditions. When it has saturated conditions, there's no idle state for any of the centers. Okay? And then we also have another aspect, which is the contention window, which is where different vehicles are fighting to send in a specific channel. So they're competing to send information simultaneously. So that's the parameter associated with communication there. And based on that, we have probability that is determined for each degeneration scenario. The other term, as I mentioned, is the speed oscillation energy, because we can measure traffic oscillation in terms of the speed variance here. Okay? Because speed varies as vehicles move. And then what we do is we go from the time domain into the frequency domain to come up with the speed oscillation energy. And our objective here is to determine the term associated with which is the speed frequency response term, which we do in the next slide here. So we derive for all vehicles using the leading vehicle trajectory. We come up with this term. I won't go into details here. If you're interested, I have a paper for this. Okay? But what we are trying to do at this point is to come up with the term that allows us to address the performance of the CACC for any degeneration scenario of the IFT. Then, in terms of string stability, so what is string stability? For those of you who attended, there were recently a few other presentations, especially if you're in the DCL group, where we saw some of this. So string stability is if you have a platoon, if there's disturbance downstream of in the platoon, then it propagates upstream. If you can dampen that, then you say that there's string stability. If the disturbance gets worse, then it's string unstable there. Okay? So here is an example where you see the space-time diagram here, which shows there are fluctuations in terms of the speed there for the first vehicle. And if you have string stability, that gets dampened, so it gets smoother here. So what that means is that fluctuation is reduced as we go upstream in the platoon. Okay? So that's what we mean here by ensuring that oscillations are not amplified. So the objective then is to obtain smooth trajectories for the following vehicles in the platoon. And in order for us to ensure first string stability, there's a particular condition that needs to be satisfied here, and this is the condition. And there are two parameters that affect the platoon performance. One is the time headway, that's one, and the second is called cutoff frequency, which is associated with the controller gains in the controller that we have. So based on that, we have an optimization function, which optimization model in which we can guarantee that string stability is achievable, but we also are able to optimize the string stability. So not only does this function allow us to ensure first that there is string stability, but we also seek to optimize it. And based on that, there is a controller structure here. So this is the controller structure that we have. And I'll just quickly illustrate what this means, where we have a vehicle which receives information from its predecessor vehicles, and then there are coefficients that are used for weighting the position, speed, and acceleration. And what that means is the following. So here you have coefficients related to position and speed. So you see those, and then related to acceleration. So what that means is the following. If you look at this table, I can explain to you what's happening out here. In the case where both the communication links exist, then we have the following weighting functions, which are determined based on the ambient traffic conditions using what are called signal to noise ratios associated with the two predecessor vehicle pairs. So that's how you determine the signal to noise ratio. So that's the basis for determining these coefficients. Now, if one of the link, so weighting coefficient simply means how much do you weigh the immediate preceding vehicle and how much do you weigh the information from the one before that. So that's where you determine that. In the next two scenarios, if you recollect, that's not the case. There's only one vehicle that you're getting information from. So you have, let's see, so you have either this case where it's this case, and then you have the other one where you're getting information from only the other one there. Or you have the fourth case where you have what is called ACC. And in ACC, the information that you're receiving is only from the vehicle in front of you. And I would mention here that in that case, as I mentioned earlier, we are not receiving information related to acceleration. So please keep that in mind. So you just receive information from the immediate preceding vehicle. Okay? Whereas here you're receiving from the vehicle preceding that as well, but not from this because the communication link is lost and so on. And this is the case where both links are run. And then in addition to that, we have the controllers which rectify the spacing error and speed tracking error, and we have longitudinal vehicle dynamics. So these are all components that are used in the steps related to determining the policy, because we adopt what is called a constant time headway policy. So we try to maintain headway between vehicles in the platoon. So that's describing the desired intra-vehicle headways. And then we have what are called feed-forward filters. And what they do is they help enhance the performance in terms of string stability and also spacing errors that are there in the steady state context. So the other aspect, so in the string stability transfer function in the controller design, so we have these terms here that go into that, and then we come up with the conditions under which string stability is guaranteed. So there's one condition for the case where there's no communication happening, and then for the remaining ones there's another condition out there. So these are all derived and we have it in the paper. And we have a two-step algorithm here. This is an example of an information flow topology where we are saying that the first one has its send functionality activated, the 0th vehicle, and then the second, which is the first and third vehicles actually, have their send functionalities activated, and then based on that there are degeneration scenarios. What that means is there may be failure here. So for example, if this is my information flow topology, I cannot have a degeneration scenario which is 10001, for example. Why? Because the IFT doesn't have the send functionality activated for this. So there are a specific set of degeneration scenarios associated with each IFT. And in the fully activated IFT case, what happens is all possible degeneration scenarios of all IFTs are possible, which means fully activated means we start with 1, 1, 1, 1. Okay. And based on that, we already talked about determining the probabilities, then the performance for each degeneration scenario, and we can now summarize all of it here in the following manner. First, offline, we have the set of all information flow topologies and all of their degeneration scenarios, because once I know the IFT, I know their degeneration scenarios, so I can determine them offline. In real time, we have the traffic conditions. We also have the platoon size. So what that means is platoon size may vary from time to time. So we have big time platoon size. There may be a vehicle added or a vehicle that's getting away because it has to exit somewhere, all of that. And then we have the IFT optimization model. So this is the place where we, based on the ambient traffic conditions, identify the set of candidate IFTs and their degeneration scenarios. For each of them, we determine the probabilities of degeneration scenarios, and that comes given the conditions that currently exist. And we look at, we determine the string stability performance for each of these scenarios. And if you recollect, we then have the expected string stability for each information flow topology, and then we do it for all the candidate IFTs. From there, we determine which of them performs the best, and that's our optimal information flow topology, and we adopt that. And under that information flow topology for the platoon, we have the case where in each instant of time for each vehicle, we'll see what is the situation in terms of where it's receiving information. And based on that, in each instant of time, we determine the car following behavior, which means what's the acceleration for that vehicle. Okay? And we do that continuously, and we deploy it using, it's a very standard rolling horizon type approach, where at some time here, delta t, and in our studies, this delta t is somewhere in the order of 40 to 60 seconds. We determine the optimal information flow topology for the next period, which is period tau. So this is in the order of 10 to 15 minutes, okay? And then within each period, we have time instances, and we use a time instance of 0.1 seconds, okay? Because time instances are continuous. I mean, if it is more than that, given how quickly things change, we are able to come up with the solution. And at each instance, what we do is we determine what is the exact degeneration scenario, and based on that, which controller needs to be used for that vehicle, and then based on that, we come up with the car follow behavior. Okay? And that's how we are able to do this. Then we go to the next period, and we move to the next one sometime before that. And ideally, if we can reduce this more, that's even better, because we get closer to real time. So you want to do that to the extent you can. So in the experimental setup, we say we use what is called a homogeneous CAV, which means all CAVs are identical in terms of their capabilities. Now, in reality, that may not be the case going forward. That would be one of the things to look at. So we have n+1 vehicles where we have the lead vehicle and n other vehicles. And so our n is 11 to 15, which means we have, we look at 12 vehicles to 16 vehicles. So we look at different cases there. And we simulate the leading vehicle's movement using some data from ngSim. And the communication success rate is obtained using the NS3 simulator, using a specific contention model there. And we test the performance of the what we call CACC optimized IFT, which is the strategy that we are proposing. And we compare it with the other two, the fixed one and the dynamic one. Now, our solution, in terms of the optimal IFT, this is the example where we have different densities of traffic here. For them, you'll see that for the number of vehicles that we have, which is 14, you'll see which of them have their send functionality activated. That's our case. And then we have it for different platoon sizes here as well. So these are the ones that we propose. And we see that consecutive vehicles will have activated send functionalities, and then in between they'll have nothing as well. So that's what we observe, and that makes sense because of how we are proposing to use these two for cooperative adaptive control. Now we are analyzing the performance. If you look at it right now, you may think, hey, they all look the same to me. Okay, because to just look at it. So let me explain to you what is happening here. So this is our proposed strategy, the OIFT, and we're comparing it to DIFT, where the dynamics are acknowledged, which means it will have to it will have to perform better than the fixed one. Okay. So in terms of spacing error, it's minimized the most under this strategy. Okay. So what does that mean? So let's look at what happens here. if you see the red boxes, there are two things that I want you to observe. You see vehicle 1, it's in green, and then it's going all the way to purple. Okay? So purple implies you're looking at the vehicles upstream in the platoon, right? So that's how this color coordination scheme is going here. Vehicle 1 to vehicle 14. So as you look at the purple ones, you're looking at vehicles which are upstream. So you'll notice that the following, the speed error, spacing error is reduced as you go upstream. When you look at OFT, it does better than DIFT, which does better than the FIFT. That's the first point. The second point you'll notice is that we are able to achieve string stability. And why is that? Because as we go further up, you'll see, so as you go to vehicles which are upstream, you'll see that the amplitude of the spacing error is reduced quite a bit, whereas here it's more. And you'll notice that under FIFT, you will not be able to guarantee string stability because here the vehicles upstream have the highest spacing error, which means they're higher than the vehicles in the downstream. So what that means is it's getting worse rather than getting better. So under FIFT, you'll notice that you are not, you can't guarantee string stability. In some cases it may happen, but there are cases where it may not. Whereas the other two, you can actually guarantee that because of the way we are controlling. The next thing is in terms of the standard deviation. This is a little more intuitive to see. When you look at the standard deviation of the spacing tracking error, speed tracking error, and the vehicle speeds, you'll see that the OFT strategy is the one which has that reduced pretty quickly compared to the other cases. You'll see here, whereas here you see you want to see the y-axis values as well. So to understand what's happening here, so this is a different set of values. This is even worse set of values. But for each of them, what you'll see is that the OFT strategy is the one which performs the fastest in terms of getting to the string stable performance. Okay. And then the DIFT strategy, and then the fixed information flow strategy. So in terms of summarizing what we did, we propose a new cooperative adaptive cruise control strategy. We call it CACC, Optimized Information Flow Topology, so at the platoon level, where we factor the dynamics of the IFT, but also factor the notion that there are communication failures that are possible under a VQV communication environment when we are looking at a CAV platoon. In the optimization model, the optimal IFT will determine the following: which vehicles should have their functionalities activated and which should have their functionalities deactivated given the ambient traffic conditions. Okay? So once we do that, what we're saying is the reliability has increased, and then the strategy of which vehicle has what controller depends on the actual instance that shows up in the vehicle. And as I mentioned before, degeneration scenarios are obtained using communication failure probabilities for that time period, which is based on ambient traffic conditions. And in the deployment context, we adaptively switch the controller continuously, which determines the car following behaviors of the vehicles in the platoon. Okay. And finally, what are some of the things which we can do, which we haven't done in this step? So first thing is, we assume that all CAVs are identical in terms of their characteristics. Of course, as you go into the future, that may not be the case. Things may change with, so that's something that we can use instead of assuming homogeneous context. The next one is, we are assuming that if information is sent, it is reaching the vehicles, intended vehicles instantaneously. Now there may be some communication delay. We can factor that, we can compensate for it and address it. I already mentioned that developing more efficient algorithms allows us to come up with a solution closer to real time, and that's always good in any problem where you're trading off computation versus accuracy. And we can use a bilayer optimization where we optimize both the information flow topology and the controller parameters to enable what we call bumpless. What that means is the following. Right now, when we come up with a solution, the controller will keep switching. So when it switches, what happens is there's a potential to have movements which are suddenly changing, which means in terms of the driving comfort, it may not be good. Okay, it is ensuring string stability, it's ensuring that that's the best string stability you can get, but that may imply that vehicles will have to do it rather abruptly. And so actually this is a study that we just finished and submitted this to the ITSC conference for this year. So in which we look at bumpless and smooth transition in the switching process. And that completes my presentation. Just wanted to point out, I mentioned some papers in the presentation, so they're listed here, and these are the papers that we have authored, and the current one is this paper, which is being presented in July at the ISWT conference. So with that, any questions?
Thank you.
So besides the swing stability, so have you also studied the plant stability?
I'm sorry, the
plant stability, the Lyapunov stability for the system. Lyapunov stability.
the Lyapunov stability.
Yeah, because if you see for this system, it's like the switched system, and actually you try to design a controller for each cases, and if you see like the system in terms of the switch system, then I mean the stability of overall system cannot be guaranteed maybe. So
Actually, what we find is the main focus here, so if I have to translate it to the real world, it's in terms of the driving comfort. Okay? And the next work that we have actually addresses that, so we actually do that. Okay? Do you have any other comments?
So you mentioned about the stability of the switch system. It's actually